Alright, we are back. Um, in the last video, we did talk about how to calculate molarity concentrations and percent by mass concentrations. Now, what I'm going to show you is something known as dilutions that has to do with the idea that we can change the concentration of a solution simply by introducing more solvent to it. So let me just walk you through the process. You could have a solution, just like a small volume of something that does contain a solute in it. So this particular solution has an initial concentration and it has a corresponding volume. And then what you can literally do is add more solvent to it. And when you do that, you're going to change, right? So here we go. We're dripping the liquid into it. In reality, like if you have it at that angle, it's going to be pouring a lot faster, than, my little graphic, depicts. But you will add more solvent to this thing, and what's going to happen is that the volume of the solution will increase automatically because you're, introducing more solvent. Now, although the volume of the solution has changed, we haven't actually changed in any way, shape, or form the quantity of the solute, right? If you look at this thing carefully, you realize we have the four, spheres right here, which represent the solute, and at the end of the addition of solvent, we still have the four spheres in there. We haven't changed anything from the point of view of the quantity, the moles of the solute. So if you think about the conversions that we talked about in the previous lecture video, namely speaking, multiplying the volume by the molarity of the solution cancels out the units of volume, right? Because molarity is moles over liter. Liter, if you multiply that by liters, the liters will cancel out and they will leave you with moles, specifically the moles of the solute. So for the first solution, taking the subscript 1 as representing the initial state, the molarity of that initial state times its original volume multiplied together give you the moles of the solute that you had in this solution. But then, when you consider what's going on here on the right side, well, now you have a new volume. This is a bigger volume that you had before, and the concentration is no longer the same because the concentration is given by the ratio of moles over volume if we think of molarity. And so this has its own molarity and now it has its own volume, but it doesn't change the fact that if you multiply this new molarity by its new volume, it will have to still give you the same number of moles because we didn't introduce any new moles of solute into the system. So what this basically means is that we got ourselves an equation to depict the process of dilution, the process of changing the concentration from a higher value down to a lower one. And it's basically this equation, N1V1 equals M2V2, where 1 stands for the initial states and 2 stands for the final state of the solution, right? So we're going to start with higher values for concentration and we're going to go down to higher values. And one thing that I want you to be careful about is that even though in this equation I'm using big M to represent concentration, this is not exclusive to molarity. We can in fact utilize the percent grams per ml or the percent mass per volume to do literally the same type of calculation with it, and I'll show you that in just a second. All right, so if we use an example to kind of depict this situation, in this case we have 15 mLs of a 1.92 molar glucose solution. But notice that in parentheses I'm also writing the percent mass per volume. So this is the actual value associated with 1.92 molarity concentration of glucose. So they're basically the same thing, except that one is in molarity units, the other one is in percent mass per volume, but they represent the same solution. And what we're going to do is we are going to dilute this thing all the way down to 350 mLs. What I want to find out is what is the concentrations, the molarity concentrations and the percent mass per volume concentrations. Okay, so we start by first acknowledging that by adding more solvent and changing the volume of the solution, we are going to change the concentrations. We're going to dilute the concentration of the solution. So we start by looking at N1 V1 equals M2 V2. And since we're multiplying M by V on both sides of the equations, we simply need to isolate the thing that we're looking for by dividing either of the sides by the thing that we don't want to keep, right? So if we look at these things, we have the initial volume, the 15 mLs, right? We also have the initial molarity, 1.92, right? So we have 15 mLs, 1.92 as the initial amount, and then the final volume is 350 mLs. The final concentration, we don't know. In fact, that's what we're after. That's what we're looking for. So what we want to do is solve for M2. In order to do that, we need to divide both sides by V2, which will change the equation to look this way, right? M1 V1 over V2. And now that we have listed what corresponds to what, it's just a matter of plugging in the values, right? So M2 is going to be equal to 1.92, the initial molarity concentration, times the initial volume, 15 mLs, divided by the final volume, 350 mLs. And since the volumes are the same, they will cancel out. And you don't actually need to change into liters. They could even be English units, like fluid ounces. And as long as the two volumes have the same units, it really doesn't matter. You don't have to change them at all. So that's kind of cool. They could be cubic meters for all we care. And as long as the two of them have the same units, we can plug them into the same formula, and the proportions will work out exactly the same way. Okay, so as far as the calculation goes, 1.92 times 15 mLs, pressing enter, and then dividing by 350 and pressing enter will give us a molarity of 0.0823. If you compare it to the original one, the new molarity is indeed a lot lower, which is expected because we are diluting the concentration by increasing the volume of the solution. Okay, the same calculation, literally in the same exact manner, will be done to calculate the percent mass per volume. We simply take in the initial concentration, 36.4%, given right here. The initial volume is still the 15 mLs, the final volume is still 350 mLs. The mLs will cancel out unit-wise, and the 36.4 multiplied by 15, pressing enter, and then dividing that resulting value by 350 and pressing enter will tell us that the concentration has been lowered to 1.56% mass per volume. And there you have it. Same equation, different types of concentration. Now, to be exact though, this equation really only works if the concentration itself is divided by volume. It doesn't matter if the volume is mLs or liters, but you have to be dividing by volume. Otherwise, it makes no sense to multiply concentration by volume and still get just moles. But since we are talking about two types of concentrations that share that particular feature, we are pretty much on a good spot. Okay, so that's the idea of dilutions. Now, the next part has to do with a phenomenon encountered in nature quite a bit called osmosis. And we're going to look at something very specific about osmosis, something known as osmolarity. But first, let me define what osmosis is. This is simply a pressure that gets generated. It's a pressure buildup as a result of having different concentrations in two compartments that are separated from each other with a membrane. And this membrane allows the movement of one of the components, usually the solvent, aka water. And it is the feature by which trees are able to ultimately build enough pressure to allow their trunks and their branches to move upwards and outwardly, right? So they build in, inner pressure, and they can actually go, the way they look, So this is not, it doesn't just happen magically. Like, you have to have a pressure buildup in there, which is a result of having different concentrations within their cells and separated by partially permeable membranes. All right, now, although one can calculate the osmosis or the osmotic pressure of compartments, we're simply going to look at the osmolarity, which is a way of expressing how much concentration is felt in a compartment. And this has to do with the fact that when you do have ionic substances, the ions are fully separated from each other. And each individual ion is counted as an individual solute particle. So if you have an ionic substance that has more than 2 ions, then your actual molarity from the point of view of osmosis is going to be 2 times, 3 times, 4 times as large. And this also has a major effect, and I kind of want to highlight this. This has biological connotation. I already mentioned trees, utilizing this feature to grow, but cells in our bodies can also experience this if we mess up our own concentrations in the cytoplasm. That basically, blood, carries through. So what you can see kind of by the shape is, what happens to the cell. So the isotonic case, iso stands for same. So this is a situation where the outside of the cell and the inside of the cell have the same concentration of ions. So there is no problem whatsoever in that respect. They're equal, they're happy. But when the concentration outside of the cell differs from the concentration inside of the cell, well, now that's when you get into trouble. So the hypotonic case, you can see that the cell is a little bit shrunk, a little bit kind of like collapsed onto itself. This happens if the concentration of ions, the concentration of electrolytes, is a lot higher on the outside of the cell as opposed to the inside of the cell, because the water inside of the cell will rush out and it will basically create a vacuum inside the cell that will cause the cell to shrink. The hypertonic case, on the other hand, you have a concentration of electrolyte on the outside that is a lot lower than the concentration inside the cell. So the water tries to rush into the cell to dilute the concentration of electrolytes within it and try to bring it to the same value as the outside. And so you end up with these cells that get swollen up. And if the difference in concentration is great enough, the pressure differential can be of such an extent that the cells will completely explode and rupture, right? And once that happens, you're in trouble. Okay, so but that's kind of like the biological outcome, right? If you really want to study that, you gotta do a little bit higher chemistry to really understand the full scope of it. But right now we're going to just calculate the osmolarity that's felt inside of a compartment by acknowledging that ions can be split up into, or excuse me, ionic compounds can be split up into ions. So look at this thing right here. We have a 1.92 molar concentration of silver chloride. Now, if you think about silver chloride, or sodium chloride in this case, my apologies. Sodium chloride is made up of one sodium ion, Na+, and one chloride ion. So in total, you actually get 2 ions out of 1 molecule of sodium chloride. So in reality, even though the molarity of sodium chloride is 1.92, the osmolarity is twice as large because you have 2 ions for every 1 sodium chloride ionic compound. Okay, so we're actually dealing with 3.84 molarity. Now, just as another example, you could actually have magnesium chloride, which has the following formula. If we have a 0.75 molar concentration of magnesium chloride, sure, that's the concentration of the compound, but the osmolarity is going to be different because in 1 molecule of magnesium chloride, we have 1 magnesium ion, 2+, and we have 2 chloride ions, as you can see from the subscripts, right? So in total, we actually have 3 ions. So the osmolarity is going to be 3 times as large than the molarity itself, right? So 3 times 0.75 is equal to 2.25 molar. So that's the osmolarity of this solution. And then, as a final example, you could have sodium phosphate, 0.37 molar concentration. This is composed of 3 sodium ions, and it is composed of 1 phosphate ion. And together, that means that you are dealing with 4 ions altogether, right? So the osmolarity is going to be 4 times as large as the original molarity, right? So if you multiply 4 by 0.37, that will give you 1.48 molarity concentration. All right, so that concludes this particular section of the lecture videos. In the next video, I'm going to talk to you about the Beer-Lambert law, which is more important to understanding the laboratory segment of this class. Okay, so here we go.